Normally some book called vectors. Okay, so we studied today operations with the matrices in general. Addition, subtraction, multiplication by a scalar, multiplication in between two matrices. What is the condition necessary to perform the multiplication, because not always is possible, and the property behind this. Okay, addition, subtraction first. Addition and subtraction. Okay. Suppose we have a matrix A. Normally, I don't know why, the matrix when you put a name is using capital letter. Well, I suppose it's a big guy. So this is the capital letter. Suppose this example is 3 negative 7 0 1 2 3. By the way, the dimension or order in this language of the matrix is equivalent to say dimension. Is 2 by 3. You see 2 rows, 1, 2, and 3 columns, right? And suppose you have another matrix capital B, okay, 5, negative 2, 8, 3, and 2. Okay, again, it's the same dimension or order, 2 by 3. I want to perform the addition operation A plus B. It's super easy. Super easy because you're adding element by element in the same position. Is 3 plus 5 is 8, negative 7 and negative 2 is negative 9, 0 plus 8 is 8, 1 plus 3 is 4, 2 plus 2 is 4, coincidence, and 3 plus 1 is 4. Wow, too many 4s. Entonces, this is the answer for the addition. By the way, it's 2 by 3. So it's important requirement to adding or subtracting. I want to see subtraction now, but it's similar. The matrix have the same dimension. See a different dimension? Impossible. Okay? Impossible. Now subtraction. Doing subtraction is easy. But subtraction is a particular example of the addition. But you have minus n, subtrahem. In the subtrahem, you change the sign. So basically is 3 minus 5, negative 2. We have negative 7 minus, double minus. Let me copy here. Negative 7 minus negative 2, no? Obviously, it's a minus 7 plus 2, no? Que es negative 5. Ok, entonces 0 minus 8, negative 8. 1 minus 3 is negative 2. 2 minus 2 is 0. And 3 minus 1 is 2. Same dimension. The only difference in subtraction is that you find the opposite sign of the matrix, any element, any entry. By the way, each element in the language of the matrix is called entries. We call entries, some book called element. The identification normally is using double subscript, no? But it's not important now. Okay, do you understand very well addition and subtraction? Yes or no? Okay, easy. Now multiplication. Multiplication, but multiplication by a scalar. And what is this scalar? Well, scalar is a number. Basically, I study now how you multiply any matrix. It doesn't matter the direction by one number. Suppose that I want to find 5A. Now who is A? Well, A is the same at the beginning, this matrix. Multiply this matrix by 5. This is equivalent to say any entry or any element inside, you multiply by 5. 15, negative 35, 0, 5, 10, and 15. Cool? Cool? Clear? Suppose another example. Suppose I take B, matrix, that one, and multiplication by 3, 3B. 3B and then is, bueno, 15 again, minus 6, 24, because 8 times 3 is 24. 3 times 3 is 9. 3 times 2 is 6. And 3 times 1 is 3. Boom. So you multiply a matrices that have dimension, is a big object, mathematical object, by the scalar. And the scalar is just individual number, the number that we are working every time in our life. Scalar, no dimension. Well, yes, dimension is 1 by 1. No? So you see, so you write like a matrix 5. This is 1 by 1, no? Okay, represent one row, one column. It's only one element or only one entry. But it's okay. Now suppose curiosity. You compute now. Curiosity. Just curiosity. You compute the 5A plus 3B. Okay, or 3B. So basically, to perform that operation, you are doing the multiplication by scalar first, and after you are adding the matrix 1 by 1. This is 15 plus 15, 30. Negative 35 and negative 6, negative 41. 0 plus 24, 24. 5 plus 9, 14. 16 and 18. Boom. Finals. And stay the same dimension or order. 2 by 3, 2 by 3, and any example. This is example case select, no? Another example case, another dimension, working exactly the same, similar. Okay, to verify that you understand this, because it's too easy, I propose one new example, but a little bit more interesting. Suppose it's given two matrices, A and B. And A is 2, 5, 184. Oh, it's easy, it's 2 by 2 matrix. 4 elements, 2 times 2 is 4. And B is also 2 by 2, 6, negative 1, negative 3, and negative 8. Let me see in my paper, negative 8. Okay, entonces I want to working with this equation, 4x minus A equal B. Entonces the question is solve this equation. Solve for x. Wait. I am confusing. B is a matrix 2 by 2. A is a matrix 2 by 2. Entonces now 4 is a scalar, guy. Entonces I suppose que everything matching under the supposition que x is no scalar, it's a matrix 2 by 2. Yes or no? Because when you multiply scalar times 2 by 2 is 2 by 2, and 2 by 2 is possible. Subtracting 2 by 2 and you get B. Okay, 2 by 2. So basically, the final answer in my problem is a matrix 2 by 2 that contains, it's obvious, 4 elements. Let me call A11, A12, A21, and A22. This is classical organization in the matrix. You put double subgroup. The first subgroup indicates the row, and the second indicates the column. For example, that element is located in the position row 1, column 1. This element is, or this entry, row 1, column 2. This is row 2, column 1, and this is row 2, column 2. Okay, I explained this idea because maybe we are using in the future, but not now necessarily in this example. When you solving the matrix equation, very similar to you solving in this equation that is 4x minus 2 equal 8. You addition 2, 4x cancel out, equal 10 divided by 4, and reduce the lower term, is 5/2, something. But in this case, matrix. Very similar. You move A to the other side, A plus B, no? And finally divided by 4. X matrix is, well, no, not yet. A plus B over 4. So division. You study multiplication, not division, but it's the same because you divide by 1/4. It's equivalent to divide by 4. Okay, let's do it. Step by step. A plus B is 8. Where come from this 8? 2 plus 6. 5 minus 1 is 4. 1 minus 3 is negative 2, no? And negative 4 and negative 8 together is negative 2. Okay, now divide by 4, is equivalent to say 1/4 here. Okay, you know very well that multiplication by scalar is you divide 1 by 1, you divide 8 by 4 is 2, 4 by 4 is 1, negative 2 divided by 4 is negative 1/2, and negative 6 divided by 4 is negative 3. Final answer. This is X matrix. Can satisfy this equation. Cool? Cool or no? Okay, easy so far. Now let's see, why not, more complicated scenario in which you have, for example, multiplication two matrices. It's different. Multiplication matrices. A matrix multiplication. Okay. To understand this, we are doing example. Suppose we have a matrix I call C. And the matrix C is 2, -3, 1, -4, 7, and 0. Okay, cool. And this matrix, the dimension is 2 by 3, so 2 row, 3 column. We have another matrix D. It's a little bit different. Okay, -1, 6, -6, 10, 5, and 8, -2. And the dimension of this is 3 by 2 because we have 3 rows, 1, 2, 3, and 2 columns. Yeah, I know if it's possible or no, multiplication C times D. So now, when you face that problem, the first thing you should do is analyze the dimension. The dimension of C is 2 by 3. The dimension of D is 3 by 2. So it must be the same dimension. This must be the same. In other words, the number of columns in the first matrix must be the same of the number of rows in the second matrix. See, these do not matching, mismatching. So the answer is impossible to perform the multiplication. No. Okay, this is the only requirement. And now, suppose you get the answer gets a matrix, in this case possible, because these 3 and these 3 are the same. No? See a different number? No. And the other no important. The important is the number of columns in the first matching with the number of rows. And the new matrix is 2 by 2. Why? Where come from 2 by 2? This 2 is this, and this 2 Que not always is the same. In this example I bring, it's the same, 2 by 2, but not necessarily. So I change the order. But it's important that this number is this number, and this number is this number. Okay? So the answer that we expect when I finish the multiplication that I want to explain right now is 2 by 2, so 4 elements. E11, E12, E21, E22. Okay? Let's do it. There are different ways to perform a multiplication. I want to explain two. Okay, I want to indicate another. Suppose I copy, suppose E11 is the element here. Is the multiplication, the first row, suppose I separate, I copy, and paste the first row in this matrix. Multiplication by the first column in the second matrix. Okay, this element is row column, row vector, sorry, 3 by 1. And this is the column vector, okay, is a 1 by 3. Oh, matching perfectly. It's a 1 by 3. Mistake. This is 1 row, 3 column. This is 3 row, 1 column. These 3 matching perfectly with this. And so when you perform the multiplication in the way I want to explain now, you get just a number, okay, 1 by 1. Okay, this 1 and 1. Okay, and the rule is clear. Let me try. The rule is you multiply. Some book call this like a dot product because it's a special kind of multiplication. It's basically, look at that. You multiply, let me use the color. This times this. You multiply, let me use another color. This times this. And you multiply using another color. Suppose yellow. This and this. Okay, then you multiply is 2 times -1 is -2. But no necessary bracket because it's just a number, no? It's a scalar, a 1 by 1. So when you multiply -30, no? -30. We go from -30, -3 times 10, no? And finally multiplication 1 times 8 is 8. And the answer is -24. I know very well that our matrix is E is -20. Okay, and we are doing now step by step. You see, wow, professor, but it's too long. No, because we are doing in the software. After I want to explain this example and so on. Suppose E12. E12 is similar. As you take again the first row, 2 minus 3, 1. But now multiply by the second column of the second matrix, no? Okay, -6, 5, and -2. Let me see who is that. Cannot clear. Oh yes, look at that. Is this part and that part, multiplication. And the ordering is extremely important. I want to explain why. Okay, so now the multiplication is 12 minus 12 minus 15 and -2. Wow, too many negative. The answer is -29. Okay, this guy is 12 minus 29. Okay, now likewise, E21, you select the row 2 of the first matrix. Okay, is this one. Let me copy, -470, -470, more, multiplication. In that case, the same, this row 1, -1, 10, and 8. Okay, let me see big picture. I multiply this row times this row. Okay, we have 4, positive 4, negative and negative positive, 70 and 0. The answer is 74. Let me continue here. And this is 74. 74. Okay, now, suppose the last one is e to 2. You suppose this example is easy because only 4 elements. Suppose it's 20 is crazy. So now you multiply one more time the row 2, okay, -4, 7 and 0, multiplication by the column 2, okay, -6, 5 and negative. Okay, this is 24 positive. Plus 35. Plus 0, no? Or minus 0, doesn't matter. 59. And this is my operation. Entonces, professor, but this is the only way to do that. No, there are no infinity way, but there are several possibilities. To illustrate this idea, I want to do it another way. Look, suppose que, and you see surprise. Suppose que I take the matrix C equivalent, copy and paste. Let me try here. I copy the matrix C again. Okay, 2, -3, 1, -4, 7, and 0. It's a matrix C. Now, instead of multiply, I take like a partition, no? Partition. What is the partition? Using, for example, no totally the matrix this, what the first column, okay? -1, 10, and 8. First of all, before to start multiplication, I need to check is it matching or not the dimension. This is 2 by 3. This dimension, and this dimension is 3 by 1. Oh yes, look at that, 3 matching. Now you expect the matrix is 2 by 1. Okay, I suppose is E11 and E21. So it's my first column. No? Let's do it quickly, but it's similar, the same idea. No? You multiply, look, you multiply -2 -30, -30, -30, -30, -30, -30, plus 8. And the answer I did before is -24. No? And likewise, 4 plus 70 plus 0, 74. And we get exactly the same, but you are doing column by column. Okay, I suppose it's not necessary repeat again for this because it's the same thing. It's another organization. So I make a partition for the second matrix by column. But another possibility is make a partition of the first matrix by row. It's another way. But I suppose it's not strictly necessary to illustrate this. Oh, why not? Let's do it at least. I don't finish this. I finish only the first column. Another possibility, I want to illustrate the different options. Suppose that you take in the first matrix the first row, only the first row, and you multiply by the entire second matrix, like that. Let me see if it's possible or impossible. First of all, I match the dimension. This is 1 by 3. So this vector is 1 row 3 column. Good. And it's a 3 by 2, exactly the same at the beginning. Look, these 3 matching with these 3, and we expect one matrix, okay, is 1 by 2. And we are doing the multiplication, this row times the first column. I did before, the answer, remember, was negative 24. And this times this, okay, the answer is negative 22. And so I did in different organization, but I obtain not the column, I obtain the row. Cool? Cool? But there's something weird behind this. And the something weird I want to illustrate in the next example is, look at that. I have no idea, surprise. Surprise. And the surprise is I have made the E. To make easy this example, I suppose short matrix 2 by 2. And another matrix F, okay, is 1, 2, 3, 4. Okay, let's do it. I want to do the multiplication, E times F. And after I'm doing F times E. To verification. To verify everything is good. Okay, so I copy my matrix 3, 5, 1, 2 times 1, 2, 3, 4. It's a 2 by 2. It's a 2 by 2 also. Matching perfect the dimension in the middle. And now we expect 2 by 2. Okay, doing. And you multiply. You multiply 5, 3, sorry, 3 times 1 is 3, and 5 times 3 is 15, and 15 plus 3 is 18. Do you follow me where I come from 18? 18 comes from multiplication 3 times 1 plus 5 times 3. 3 times 1 and 5 times 3. Now remember, you multiply element in the row by element in the column, no? Likewise, I want to do fast. This is 3 times 2 is 5. 3. This times this. 3 times 2 is 6, sorry. 3 times 2 is 6. And 5 times 4 is 20, is 26. Now moving on to the second row. 1 times 1 is 1, plus 2 times 3 is 7. Finally, 1 times 2 is 2, and 2 times 4 is 8, and 8 plus 2 is 10. Do you understand the multiplication, or I repeat again? No. Okay. Yes. Yes, what means yes? I need to repeat again, or you understand? Understood. Okay, understood. Okay, Emily T is understood. Okay, that's a surprise. Suppose I do the multiplication E times F. So I swap. I change the order. Suppose we have 1, 2 here, 3, 4, and 3, 5, 1, 2. The dimension is the same. Matching perfectly. We expect 2 by 2 matrix. And let's do it. Is 1 times 3 is 3 plus 2 times 1 is 2 F5. Wee. And you see again the first is 18, now F5. Wow. Now multiplication is with the second row, with the second first row and the second column, sorry. 5 plus 2 times 2 is 4 is 9. 9 plus 4 is 13. And 15 plus 8 is 22. Oh, entonces different. Entonces, en general, E times F no is equal F times E. Okay, entonces be careful when you are doing multiplication, because this doesn't work like a scalar or like a numerical value we study in algebra every day in our life. No. The order is important. Therefore, suppose you have a matrix A and you want this to multiply by B. Pero entonces, and that's C. Pero entonces, what is the order, guys? Is in this order or in this order? This is important, specification. And this, when this in this order, is the name is post multiply, because it's after. And when it's in this order, it's pre multiply. So you need the specification. If you, so when you manipulate an algebra of the matrix, you need to specification si es post multiply or pre multiply. Okay. Okay. One more example of the multiplication to matrix. Suppose multiplication this matrix time multiplication this matrix. The first thing is analyze dimension. This is 3 by 2, 3 row, 2 column, and this is the same, 3 row, 2 column. And you analyze this number and this number. It's different. So we cannot apply. We cannot apply multiplication in this case. Okay? No, impossible. Impossible. Very important, guys. You verification the dimension. So you are doing using the software, and you indicate after I want to explain the software. I want to cover the theoretical part first, and after I go to the algebra, I explain in detail how you perform any multiplication, because it's too tedious, you know, it's too long. You can, and the idea is clear. In the lab online in Alex, you need to perform a lot of operations. No, you open your algebra and you are doing in the computer. And the written test, no. In the written test, you need to indicate, but in some examples, I specify in the review package, because they are another gets too long, stupid, too, very crazy. Okay. So now, I suppose that so far it's a little bit clear multiplication. I want to introduce a new idea, que es inverse matrix. Inverse matrix. Well, inverse matrix is, suppose that we have one matrix, matrix A, capital A, que I suppose que es the original given in the problem. And the inverse matrix, the symbolic way, the notation we use in mathematics is like that. inverse matrix. This is inverse. But this is no exponent. This is the symbolic way to indicate it's inverse. This is very similar when you're studying algebra, the function and the inverse function. Okay, of course, this is not equal 1 over f. Is when you interchange domain and range. This is domain, this is range, and this direction is f, and opposite direction is inverse function. Similar idea. A symbolic, totally symbolic way. So the majority of people using this symbol, but you can put in English inverse matrix, that's it. It's okay. The requirement to the inverse exists. The inverse exists in two conditions. Only for the square matrix. What means square matrix? One square matrix, 2 by 2, 3 by 3, no? 4 by 4, so same amount of row and column. Okay, it's impossible find the inverse matrix of the rectangular matrix, suppose 2 by 3, no. Find the inverse, no. Impossible. No, to be square. Only the square is possible. Another specification is non-singular. Okay, maybe you don't understand very well, but I promise I want to explain in few minutes. Non-singular. Okay. But the most important, the definition of the inverse definition is when you multiply any matrix, any A, the original, by time is inverse. The answer is identity matrix. I want to prove it in one example right now. And by the way, surprise, is the multiplication, the inverse matrix times A. Wow. In this case, you can swap inverse matrix. This is the only, well, not the only, but it's a most popular example. When you multiply any matrix times its inverse, you can interchange, and the answer is identity matrix. Remember, identity matrix is a matrix like that: 1, 0, 1, 0. It's identity matrix dimension 2 because this matrix 2 by 2. Identity matrix dimension 3 is 1, 1, 1, and the rest is 0. And so on. No? Identity matrix dimension 4. In this case, 4 element, 9 element, or entry, 16 entry, okay, or element. Okay, this is the idea. Let's see example to illustrate much better, more clear this idea. Suppose that I have one matrix. Okay, the original matrix is 3, 5, 1, 2. So one magic way I found the inverse matrix. I promise I explain after how you find inverse matrix. Okay, in this case, 2, -5, -1, and 3. Well, professor, where come from this? No, I don't have no idea. It's given. You say, you say want to prove okay, this matrix is inverse each other. Okay, let me try. Multiplication, 3, 5, 1, 2, time 2, -5, -1, 3. And first of all, checking the dimensions, see matching or not. 2 by 2, 2 by 2, of course, matching perfectly. And the new matrix is 2 by 2, so good. Now let's do it. Remember the multiplication. You multiply first row and first column. 6, 2 times 3 is 6. Plus or minus, depending on the sign. Well, it's plus -5, because 5 times -1 is -5, and 6 minus 5 is 1. Now the second element is first row and second column is -15 and +15. Excellent. This next is second row, first column. 2 and negative is 0. And 2 times 5 is negative 10. Okay, let me see. This times this is, is 1 times negative 5 is negative 5 plus 2 times 3 is 6. F1. Oh, it's identity matrix dimension. Let me try, and the professor explained me when you swap the order commutative, not necessarily the same. No. But let's try in this specific example, no? 2, negative 5, negative 1, 3, and 3, 5, 1, 2. Let's do it again. Is 6 minus 5, 1. Is 10 minus 10, 0. Is negative 3 positive 3, 0. And this one is negative 5 plus 6, 1. In this case, by coincidence, it's the same. And this is the definition of the inverse method. Well, okay, I understand. But welcome from this inverse method. What is the formula to find this? The formula I want to explain. The formula is very, very, very complicated when it's bigger than 2 by 2. But I want to explain the particular shortcut to do 2 by 2 that's the most popular. And when it's 3 by 3 or 4 by 4, I want to explain how we can put that. Look. Suppose the formula for 2 by 2. Suppose in general, what matrix A, B, C, D. 2 by 2. I want to explain the formula to find the inverse matrix in 2 by 2. Okay, the formula says 1 over AD, A multiplication by D, minus B times C, and we get in the matrix D minus B minus C and A. I want to explain the easy way to remember this formula. Well, first of all, you compute this scalar. Okay, in our specific example, I come back to our specific example, get 3, 5, 1 and 2. Well, okay, you multiply, it's 1 over A is 3, multiplication by D get 2, minus B get 5, multiplication by C get 1. So 1 over 6 minus 5 is 1, and the answer is 1. That is the reason in our example is invisible, this factor. So now the easy way to remember that, you interchange A and D. I put A in the place of D, I put D as the place of A, swap the position. And C and D no, stay the same, but I change the sign. As you want to find the inverse matrix, remember, you multiply by this factor, okay, in this example, 1, nice. You interchange this guy, 2 and 3, and 5 and 1 stay the same, but opposite side, combo, and you get this answer. Super easy. Super easy. Bueno, professor, equals 3 by 3, 4 by 4, more complicated. So I want to propose one idea. Of course, this idea is too long process, but remember we have software. Okay. So now another way is you take the augmented matrix in which you copy the matrix A, augmenting, put the line, vertical line, identity. And you apply reduce the row echelon form. You know how you compute in the computer, right? And when you are doing this, magically happen the identity matrix swap here. In this right-hand side we have the inverse matrix. In conclusion, In conclusion, suppose we are doing now in the software. Suppose that intentionally I put 3, 5, 1 and 2, and you put identity matrix 1, 1, 0, 0. And when you perform the famous reduce row echelon form, you get now here the identity matrix 1, 1, 0, 0. In the right hand side, you get 2, negative 5, negative 1, and 3. Entonces it doesn't matter what dimension is, if 3 by 3, 4 by 4, you copy together the original matrix is given in my problem plus the identity matrix. You perform the reduced row echelon and automatically you get the inverse matrix here. Okay, going to take a break a little bit the theoretical part. Let's move into GeoGebra. I want to explain in detail, step by step, the most important operation that we are studying today at the beginning, right? Okay, suppose. Okay. Wow, I have too much students. Okay, let me open GeoGebra. Cool. I want to share the screen because I want to explain step by step everything. Switching to GeoGebra Classic. Do you see GeoGebra? You see? Okay. Cool. Okay, let me see what example. Okay, at the beginning, but we are doing fast because the computer is fast, no? The only problem is typing any number, but it's okay. Suppose. Well, okay, when you open that, this is the environment. You click here and you go to the view. In the view, you select the window, algebra, cast, no graphic, no, and spreadsheet. Okay, the spreadsheet working like a matrix editor. You put a number here, it gets countable. You transfer to the algebra and you solving everything. This is algebra. Okay, suppose the beginning. The beginning, remember, was the matrix 3, negative 7, and 1, 2, 3. Hey, that's the beginning of our lecture. And the matrix BF5, and negative 2, one more, 8, and 3, 2, and 1. Typing, you select the array, you declare it like a matrix. Remember, right click, create matrix, immediately you see, wow, here, beautiful. And why not rename? Because in my paper, I remember that the name of this matrix was capital A. Cool. And the name of this matrix is capital B. Guys, I don't want you see, no, professor, my GeoGebra, I don't know working with this. I explain detail now. I record the video, you watching the video, and you, so you are not here. Well, you learn by yourself. Matrix. And the name of this matrix is rename B, capital B. I go to the cast. In cast, I say A matrix plus B matrix. and present. Boom. And you see exactly the same. 8, 8, negative 9, 8, 4, 4, 4. You remember 4, 4, 4, no? Oh, let me see. I made a mistake. Yes. Hey, what the hell? Hey, I make a mistake. Hello. This matrix is incomplete. Again, redo again. Create matrix. Okay, so I delete this guy. And how I delete? Delete this here, delete. I repeat again the process. Well, no. I rename. This is now a matrix. You make a mistake. Hey. Okay, this is A plus B. Fortunately, we are doing behind. Guys, it's important. Do behind and double checking with the software, no? Enter. Wow. A negative 9, A 444. Exactly the same. We're doing the piece of paper. Okay. Now, I remember also that we are doing operation with the scalar. And the operation with the scalar was 5 times A plus 3B. I press enter. And the answer, you remember 30, negative 41, 24, 14, 16, and 18. Do you remember that? Cool. Now, let's practice using the software, of course, multiplication. Entonces I using the same example that we're doing the board by hand. If you want, you delete that part. If you want, you delete. If you want. So I personally, I like so much. New example, clear the house. Clear. Okay. Now, suppose the matrix C is 2, negative 3, 1, negative 4, 7, and 0. This is my matrix C. Maybe good practice is immediately you finish to type the number, you convert to the matrix object and rename. This is C. This is not mandatory. So you like this name, matrix 1 M1, it's okay for you. Likewise, I have another, okay, negative 1, negative 6, 10, 5, sorry, enter much better, 8, and negative 2. Okay. Okay, now finish. Select the number. Declare like a new object, matrices. Y I rename. Like D, ¿no? Es the name que we use in the piece of paper. And the whiteboard. Rename. Copy D. And ready to apply multiplication. Multiplication was, in CAS, you go to CAS and multiply C time is shift 8 is period D. Okay, bam. And we get the new matrix of multiplication, that by the way is 2 by 2, negative 24, negative 29, 74, and 59. Cool. We are the best. Now let's practice now inverse matrix. Suppose. Okay, we have the original matrix. In this case, I want to type in here. This is 3, 5. Okay, the matrix. This is the matrix A in our example. rename matrix A. Click OK. And I go to the gas, and gas have a special operations, case inverse. But in the language of the GeoGebra is no inverse, is invert. I don't know why. Don't ask me why. Invert. There you go. Invert what? Invert matrix. What matrix? One of the matrix I call in my problem A. Boom. And this is 2, -5. Let me check it. Oh yeah, 2, -5, -1. Okay, super cool. Let me try to copy this here, because this is the inverse. The inverse is 2, -5, enter, -1, and positive 2. Okay. Positive 2. I convert to the matrix. Yeah, I want to change the name. Maybe, I don't know what name. You can call any name. Call A1. A1. Capital. Yeah, I know that A1 is inverse. Let's do the multiplication. Multiplication A times A1. Wow. You see is the identity matrix. In the other direction is A1 times A. Always is identity matrix. Let's practice the another procedure I explained. Look, let me show you. Suppose now I copy. This is fantastic because you select here and you copy, and you select here and paste. It's similar to the Excel. And you include here the identity matrix 1, 0. It's a matrix matrix, no? 0 and 1. Select this. Create like a matrix. In this case, not square, it's rectangular. Entonces this I call augmented matrix, ¿no? Rename. Let me call augmented. AU nada más. Only AUG. No, AU. Bam. Now, here, you remember, you are doing similar to the last class. You could reduce the row echelon of the matrix. What matrix? AU. You present it, bam. You see how the reduced row echelon convert the left part and the identity matrix if the right part is identity matrix and the original to the inverse matrix. Super fantastic way. Yes or no? Everyone follow me? Everyone understand? And this is just the beginning. And this is just the beginning, because now I take advantage of this fact to illustrate very, 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 very well how we can using this idea for solving system of equations using another way, using inverse matrix. Let me come back to the whiteboard, and I want to illustrate the new idea. Okay, there you go. Clear. Do you see whiteboard? Suppose, to illustrate this, I suppose example, no? Suppose that we have system 3x minus 2y plus c equal to equation 1. X plus 4y minus c equal 6 equation 2. And 2x plus 5y minus 2c equals 6 equation 3. Okay, now this is the determinant system 3 equation 3 or no. Maybe you can solve it in relatively easy by elimination by hand. Pero no. We study matrices. Yeah, matrix fantastic, no? Because maybe 3 by 3 is acceptable. However, 4 by 4 is crazy. And 20 by 20 is impossible by hand. However, using computer, yes. Okay, so the organization is different. Because so far, using reduced function alone, you take the augmented method. No augmented method. Okay, let me try to write this system in matrix format. Matrix form. You declare one big matrix. It's a matrix A. Okay, this matrix A is 3 minus 2, 1, 1, 4, negative 1, 2, 5, and negative. This matrix only the matrix formed by coefficients in front of the variable. It's obvious que es square matrix 3 by 3. Okay. Now, I declare one weird thing is capital X. Capital X is a new matrix, actually is no matrix, it's a vector, is formed by the variable X, Y, and Z. So when you call capital X, it's a column vector 3 by 1, is formed by the variable X, Y, and Z. Depending, no? See, we have 4 variables X, Y, Z, W, always, no? And B. Who is B? No, B is the right-hand side number. B. B is the right-hand side number, que is 266. Okay, again, is a column vector. But some people say, well, no, I know operation with the vector, professor. I know that the vector is possible multiplication, addition, subtraction, multiplication. So si you multiply A matrix times capital X, let's see what happens. This is 3 by 3. This is 3 by 1. Okay, cool. Matching perfect dimension. And you get another matrix, B, is 3 by 1. Where come from this 3? This 3 is this 3, and this 1 is this 1. Okay, now this is the same system of equations que consists of 3 equations, but we can condense in a matrix form in one equation. Of course, this equation is multi-dimensional, no? But it's okay. So using algebra, let me try to solving very similar to the one elementary equation that we solving in intermediate algebra, 2x equals 4. Bueno, you divide by 2 both sides. And to say 4 divided by 2 is 2. End the story. We are solving this equation similar to this. I copy. AX equal B. But the problem, professor, is that I cannot divide it by matrix. No, the division of the matrix is not defined. Well, but we define something similar to the division que es inverse. Let's suppose, bueno, entonces I want to multiply by inverse, que es somehow the idea behind this division by 2. Suppose que I multiply this equation, but be careful with the multiplication because I know that maybe you post multiply or pre-multiply. Let me try pre-multiply by inverse. Okay, both sides. Yeah, I know that when you multiply an inverse matrix than the original, give me the identities. times x equal inverse matrix times b. Cool? And when you multiply the identity matrix times any vector, identity matrix suppose que in this case 1 0 1 1 1 0 0 0 0 0 0 multiplied by x y z. It's obvious that when you multiply here down here is x. When you multiply this times this is y, and when you multiply this times this is z. So identity matrix, in my mind, working like a B1 dimension 3 by 3. And when you multiply 3 by 3 and 3 by 1, you get 3 by 1. Okay, actually, is, so this is equivalent to say capital X. Okay, is by definition x, y, z. And this example, no? Another example get 4 dimension, x, y, z, w, etc. Entonces now, this is my formula. My formula is x, que es de set, right, like a column vector, x, y, and z, que is my unknown, is you could perform the multiplication inverse matrix A multiplication by. Wow, fantastic. But this is too long process. Doing by hand. So I propose to you doing in this example. Let's come back to algebra, and you erase everything, start at the beginning, and you define your matrix A, you define your matrix B, you perform this operation, and when you perform this operation, we expect one column vector, okay, we have one number here, one number here, and one number here. Therefore, x is equal to this number, y is equal to this number, and z is equal to this number. End of story. It's another approach. It's doing. Do you follow me? Do you understand the thing I want to try now? Okay, it's doing. It's doing. Okay. Switching. Oh, no, good. Okay, I can fix it. Okay. Okay, cool. Do you see the algebra? Do you see or no? Okay, guys. I want to clear everything. Clear house. New house. Okay, now I can change the width of the cell, similar to Excel. Because I want to type in the matrix A, get 3 in this example, -2, +1. Enter. 1, 4, and -1. -1. Enter. 2, 5. A matrix A and the product. I create like a matrix. Okay, right click, and you now rename or not. Either way, it's up to you. Copy. Now I define B. B is a column vector, okay, followed by the right hand side number F2. I create this new vector. I want to call B. Rename B. Now, see, I want to do short. I copy here in the cast, invert. It's a notation. Invert matrix. We have invert function, invert matrix, no? Invert matrix. A, multiplication. Hey, well, I did that. Okay, this is horrible. Doing by hand is crazy. I want to copy. Okay, what's good? Because I copy. Let me see. Control select, Control C, and Control B. No? Control B. There you go. Now multiplication by B. Okay, this matrix obtained was the inverse matrix of the original. Look like horrible, no? Now press enter. And we have a solution of the system que I create for you. Nice, funny, 1, 2, 3. So I say column vectors x is equal 1, y is equal 2, and c is equal 3. Ooh, cool! Do you like? Do you like? Okay. Super cool. Yes. Okay. Entonces, I promise que the review packet. We continue that part. We continue. So now the rest of the time that we have, I want to explain another topic. Que es very, very related to this. It's no completely different. No. It's another approach for system equation, but different. I don't know why some people prefer that way. Actually, in my opinion, no. But I respect opinions. Some professional engineers say, no. I don't like matrices. Okay, I respect. I love matrices. However, some people prefer doing in another way. Okay, of course, we can use the computer, no? But this is determinant. Let me explain it there. Determinant. 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 Let me explain it there, guys. Es easy, pero es confusing. Determinant is, it's a function, in my opinion, it's like a function que connecting the set of all square matrices. When you're talking about square matrix 2 by 2, 3 by 3, and so on, no? 4 by 4, connecting somehow with the one real number, one value, que belong to the all real number, fancy all real. Okay, so basically we can compute determinant only for the square matrix. I want to explain in detail now. Suppose, and the notation that we use to determinant is similar to the matrix, but no. Is you put a bar, vertical bar, similar to the bar that we use in actual value. Remember actual value 3 is actual value, no? Actual value -3, positive 3, and actual value 3. But no. It's completely different meaning. It's a bar, vertical bar, but inside we have no one number. We have array. We have one number that belongs to the square matrix. So we can compute it 2 by 2. We can compute it 3 by 3. Suppose another example. Okay, 3 by 3 determinant, 2 by 2 determinant. Okay, so I want to explain what is the operation connecting this and this. What is the formula to compute that? Let me start for the 2 by 2, que es super easy. 2 by 2 is super easy. You detect the 2 by 2. Okay. You say you multiply this number and this number, and don't change the sign. And you multiply this number times this number, and you always change the sign. Change the sign or multiply by -1. Entonces, 2 times 5 es obvio que es 10. And 4 times 3 is negative 12. Because you multiply 4 times 3 is 12, but you change the sign. So the diagonal is going down. No, don't change the sign. The diagonal is going up. You change the sign. Or you're introducing artificially extra negative 1. Entonces the answer is negative 2. This is the formula, right? You are familiar a little bit with this formula because in the inverse matrix, in this moment, I don't anticipate this idea. You multiply this number and this number is AD, and you multiply this number is minus BC. You remember when you are doing the formula for the inverse matrix was 1 over AD minus BC, and you copy here something like that. You interchange this guy. So it's DA, and this stay in the same place, B and C, and you change the sign. This is the formula for the inverse matrix in 2 by 2, of course. And I don't say in this moment that this part is reciprocal. So more generalized idea is to find the inverse matrix. To find the inverse matrix, you are doing something here, D minus B minus CA, and you divide by the determinant of it. Okay. Okay. Let's practice a little bit. Let's practice, for example, 2 by 2 again. Another 2 by 2 example. Another 2 by 2 example. Let me see. Let me try to find. I have another 2 by 2. Okay. Suppose. Another. Suppose 4, 5, 2, 3. And this is 12 minus 10. Okay? Super easy. Super easy. And what about 3 by 3? Super complicated. Super complicated. But I try to explain. Okay, 3 by 3. 3 by 3, we using one formula. It's called cofactor formula. Cofactor formula. Okay, I try to explain, but it's a little bit, it's much better seeing the example, no? But let me try. Suppose it's 3 by 3. 3 by 3, of course, we have 9 elements, no? A11, A12, A13, A21, A22, A23, A31, A32, A33. The beauty or the magic of this is that we can using to cofactor formula expand using any row or any column. The column or the row that you prefer. How do you know what I select? Well, you don't know. But depending on the example, I recommend maybe using a specific row. So for example, the majority of the students using the row 1 to expand. And to expand, you start for the first entry, get this, and you copy. A11 multiplication by cofactor 1. They want to explain it. Who is the cofactor 1? The cofactor 1 formula is plus or minus, depending on the position. And the position, there are many ways to memorize this. Plus, minus, plus, minus, plus, minus, plus, minus, plus. So we are doing this guy, no? And this guy post. One way is you take, for example, Let me erase that part. You take -1 raised to the I plus J. And who is I and who is J? Bueno, it's the position, no? And this is a formula. It's IJ, IJ, IJ. Si we, for example, we computed the C11, que es the cofactor location, and the row 1, column 1, is -1 raised to the 1 plus 1, because 1 plus 1 is 2. And it's even, no? It's even, entonces es positive. Look, it's another shortcut to memorize this, okay? You start for the positive, you alternate negative, positive, negative, positive. It's another way. It's obvious. Multiplication, 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 multiplication by the minor ij. And the majority of the students confusing cofactor and minor because it's similar. It's look like the same, except the sign. Minor have no sign. Well, have the sign of the computation, but cofactor you adjust the sign according to this rule. So what is the minor? This is cofactor. Let me put the name to don't confusing, and this is minor. Minus is the new determinant que es formed when you delete mentally in your mind. You delete. See, suppose that we're working with this. You delete mentally the row 1 and column 1. Oh, entonces stay alive this element. And this is the minor. And this is the minor. Okay? But don't worry, in the example you see clear, no? Okay. Let's continue moving. I go now to the second element. This is minus A12 cofactor 1, 2. Well, actually plus. Pero cofactor is negative in this position. Look at that. Finally, A13 cofactor 1, 3. I suppose you don't understand very well. No. It's confusing, professor. Very, very, very confusing. Therefore, I propose you a couple of the examples. Let's do it. Why not? To understand much better, and also don't frustrate for this because you can compute this in algebra. Okay. Suppose this example. I promise in the review packet I have a lot of problems. Compute that. And this is the idea, guys, suppose que son professional like determinant. Because this automatically you associate with the one number. You say no matrix, no, it's abstract. No. You this square matrix, you associate with the number. Okay. Suppose I am beginner. I have no training in this part. I assume expand using the first row. Okay. So 1. This one is this I copy. Multiplication by the minor cofactor is 3, 5. You delete mentally in your mind, your row 1 and okay. You delete mentally this and this. And this is the minor. 3, 5, negative 2, 0. And this is the minor, but the cosine, the sine is a positive. So they are perfect coincidence, cofactor 1, 1 and minus 1, 1, because the coefficient here is positive 1. Cool. Now I move into 4. And 4 is negative 4. Negative. Because I know that the cofactor 1, 2 is equal minus 1, 2. Because it's, negative 1 raised to the 1 plus 2 is 3, entonces negative 1 raised to the third power is negative 1. multiplication by the minor. In this case, 1550. Because now you delete this. Oh, you delete this guy and this guy and stay alive. 1550. Cool. I finished. No. Because we have 0. Okay, the last element. But 0 is 0. Shh. A 0 is nothing. Okay, by curiosity, I put the 1, 3, 5, negative 2. Therefore, because I delete in my mind this column and this row, 1, 3, 5, negative. But this is 0. Hello, professor. Entonces now, I don't care this guy. Okay, entonces now, this guy is 0. It's gone. And you focus in the rest. And the rest is, let me show you. I can delete mentally this because 1 is invisible multiplier. And you multiply this and this, no change the sign, and this and this, and you change the sign. Es obvio que 3 times 0 is 0, and this is 10. Yes or no? Negative 2 and positive 5 is negative 10, but the professor explained me that when you multiply and the diagonal is going over, you change the sign to the positive. Cool. Minus 4, multiplication by something. This time this, positive, and this time this, okay, is negative. And 5 times 5 is negative 25. And multiplication now is 10 plus 100, no? 25 times 4 is 100, negative times negative positive, 110 is the answer for the determinant. But you see, wow. I am not 100% sure because, okay, I would like that part in which this part disappeared. So to expand determinant, I take advantage the 0. I can see 2 0 here. So now my question is, professor, you say okay, to expand the determinant using the cofactor formula, you can use any row or any column. Okay. Suppose que I am using. It's a problem. Do you hear me, right? No problem. Do you hear me or no? The connection, okay, sorry. I don't know, some people try to get in. Okay, this is the most important moment. Okay, do you see whiteboard or no? Okay, one idea is, well, professor, would be fantastic, expand this determinant, no using like a beginner, the first row, the third column. Oh, why? Because we have 2 0. And the only cofactor that have value is in the 5 part. Okay, so now, let me try. Of course, you're using this guy as 0, The important, you focus in the 5. 5 is located in the position row 2, column 3, no? Okay, row 2, column 3. And 2 plus 3 is 5. And 5 is odd number. So it's negative. Okay, it's negative. It's negative 5. Negative 5 times something. And the minor associated with this game is you delete mentally. What the hell? You delete mentally. The row 3 and the row 2, sorry, and the column 3, and stay alive only in alive 1, 4, 5, and negative 2. Do you understand the idea or no? Okay, I get the focus with this call inside the lecture. Shh. Okay, do you understand or no? No? Yes, okay, cool. Okay, so now let's do it. Let's identify. And remember, you multiply this guy and this guy. No change the sign, it's negative 2. And you multiply this guy and this guy is 20, no? 20. But this is negative 20, negative 20. And entonces negative 5 multiplication by negative 22, no? And negative positive, and the answer is exactly the same. Do you see the beauty of this? Do you see the beauty of this? Okay, entonces, what is the criteria to expand? Well, so you don't know, every student normally using the robot. However, suppose a big determinant, big, que es, 20 row, 20 column. And you wanna like, what is the most convenient way? The most convenient way is using the column 3. Because in the column 3, you have 2 zeros. So and you simplification, this determinant is 3 by 3 and only 1. Okay. Now to finish today, I want to show you this example in GeoGebra. Okay. In GeoGebra now for the determinant, and I promise next class we study the application of the determinant for solving system of equations. But no now. Now is, let me switching to GeoGebra screen. Boom. Do you see that? Okay, new example. Create the habit to clear house. And you copy in any place, guys, in any place. You copy 1, 4, 1, 3, 5, 5 again, negative 2. Okay, ready. You select that, you right click, you create matrix, square matrix. Okay, cool. And you type in here NCAS. Okay, the CAS, is the block. Okay, are doing a lot of fantastic operations. And you type in determinant. Oh, there you go. You don't feel to typing and use determinant or matrix, right? A determinant matrix, in this case, is the matrix M1. Let's enter, and the answer is 110. Do you see that? So don't complicate your life. I explained the idea to do by hand. However, normally, so by hand, I ask you in the test only when it's 2 by 2. And not always, depending on the problem. Okay, I specification in the review package, that part. The next lecture, stop for a moment. Next lecture, we continue a little bit the application for the determinant. Okay, and I suppose I start the review package for that one. When I'm switching on cancel, wait a second. This is stop sharing. Do you see my face? Okay, I try to explain. Next lecture, we continue determine applications and start review package. I will send Monday the review package. We spend maybe 1 week doing the package, and we are ready to do the test. I don't remember exactly what is the due date, but don't worry. You see thank you, thank you. You see in the Alex, what is the due date I fixed? I don't remember. I can change si es necesario. Okay? Bueno, good afternoon, everyone. Bye bye.